Okay, our final speaker in the morning session is Professor Ling. She will teach us how to build quantum spacetimes with BCFT Legos.
I'd like to thank the organizers for giving me this opportunity to speak here. I feel a bit embarrassed because lately, I think in the course of a month or two, I gave this talk maybe 6-7 times, and I can see that a part of the audience have already listened to this talk, and I apologize. So I don't, as far as our project is concerned, we do have something new to add, and I hope it would come out fairly soon. But as far as the talk is concerned, I didn't add many new ingredients. So please forgive me if you feel that you have heard this and it's boring. But I hope that at least I might be able to make it clearer since we have a bit more time than in other talks that I've given before, where usually it's a half-hour talk and I've expanded it to a 1-hour talk. So this work is really a series of work, a program that we have been pursuing since almost 4 to 5 years ago. And as my title suggests, we're trying to build up space-time with some basic building blocks. When we talk about space-time, we really mean quantum field theories defined in space-time. And we're hoping to construct these space-times using basic building blocks that we call Legos, which is paying tribute to a very famous piece of work written by Grothendieck, a visionary piece of work, what he called Lego Teschmuller, which are the basic building blocks to build up arbitrary surfaces. And here, in a large class of two-dimensional CFTs, particularly rational CFTs, we show that basic building blocks for the field theory path integral is some boundary conformal field theory correlation functions, and therefore we call that the BCFT Legos. They will be form the fundamental building blocks from which we construct a path integral. Why do we want to do that? The reason why we wanted to do that is basically inspired by the tensor network program to construct, to represent or to simulate field theory using tensor networks. And if you think about what tensor network is, it is basically to cut space-time into pieces and then put them back together. And that was what got us into this journey to look for what would be whether we can represent these basic building blocks analytically. And for this class of CFTs where we think we have some success, the techniques that was involved developing some RG operator RG operator that is inspired by very recent studies in generalized symmetries. So this is a work here. We spent a couple of years trying to understand an RG operator, finding their fixed points. And then in here, we give substantial with Chen Gong and Chen Ling. And so here with Chen Ling and Hao Chen, Taixin, who is in the audience, Shen Ce, and Ruo Shui, we developed this RG operator and I try to understand the properties of an RG operator. And then later, we find solutions for fixed points and we tested it numerically, substantially. And this is work done with Chen Gong, Chen Ling, and Zheng Cheng. So we tested it to make sure that our theoretical proposal gets very strong numerical evidence that it is correct. And it is not only correct, it is very, very efficient. And then we pushed this program. So we were working in rational CFTs. And when we tried to push this program to irrational theories, then a bulk, then it appears to be connected to the ADS CFT correspondence. And this is work done with Yiquan, Chen Ling, and Bingxin that we wrote 2 papers at the beginning of the year. We'll write a bit more to explain some particular pieces of dictionary in the ADS CFT, such as Didi bar deformation, further in some upcoming work. that we are not going to today, but I think we do have a little bit of success in actually understanding I believe this program would have something more to say about the ADS-CFT correspondence in general. So kind of a long introduction, but let me motivate a little bit more what this program is about. So why did people started talking about tensor network, connecting tensor network with the ADS-CFT correspondence, which was the original motivation for me to study this problem. So as Professor Chen Ming has already discussed in his talk just now, there is this very famous Ru-Takanagi formula in the ADS-CFT that tells us that the entanglement entropy of the CFT can be computed using the some minimal surfaces that go into an antidistant space in one higher dimension. And so essentially it says that information about entanglement is encoded geometrically in the gravity dual of this theory. So it was observed by Brian Swingle back in 2012 that this picture of entanglement, expressing entanglement as a geometric data is very familiar in the condensed matter literature, where they figured that if you want to write down wave functions, when you try to solve for wave functions of ground state wave functions of a many-body system, what you can do is to write down a numerical ansatz, what they call the tensor network, and the tensor network, the ansatz of the tensor network, the geometrical connections of these tensors is actually encoding the entanglement structure of the ground state wave function that you are working on. And numerically, so when you try to look for ground state wave function, then what you do is that you numerically try to optimize these tensors, try to lower the energy of the expectation value of the energy operator until you get the lowest value possible. Then the tensors would is supposedly producing an approximation to the ground state wave function. Well, the bottom line is the following. So it seems that aside of the numerics, it seems that this picture is very similar to the Ru-Takanagi formula. So people started asking the question, maybe tensor network is a way of constructing a microscopic map between CFT degrees of freedom and gravitational or geometrical degrees of freedom. And so the trick is all the entanglement data is basically hidden in these tensors, and these tensors is telling us about the shape of an emergent space-time. So this is a wonderful idea because in the past, ADS-CFT seems like a black box. You compute something in CFT, and then you compute something in ADS, and they match. But it is very difficult to understand what goes on behind the scenes. Tensor network seems to provide a framework that tells you what is how to repackage the CFT data into geometrical data. So this sounds great, except we don't know how to write down these ansatz and in fact solve for the tensors in the tensor network. This is precisely why I was referring to the precise numerical tricks that people have to obtain these tensors in real life computations. So there are two main difficulties. Difficulty one, what would be an appropriate ansatz for this graph so that it is the best representation of the wave function or path integral that you're interested in. You can see that this is already a very difficult problem. Whenever you choose a discrete graph, then people would say you break lots of symmetries. And so there is no reason, if you break all these symmetries, are you sure that there would be limits, a continuous thermodynamic limit where you can return to the continuous field theory? There is no guarantee. Secondly, even if I have an appropriate choice of graph, what do these tensors take? So people usually resort to a numerical optimization, but then the result has, you don't really understand the result of the optimization. It still looks like a black box to anyone who is used to computing things analytically. So those numbers just looks like magic. When you optimize this tensor network, you somehow recover a mirror tensor network or whatsoever that recovers lots of details of maybe the CFT and maybe even say something about ADS space, but it just feels very mysterious what these tensors are. So in this talk, I hope I will be able to convince you that at least in the case of two-dimensional CFTs, I would be able to tell you how to compute these tensors analytically. And that that when you try to construct path integrals of a CFT, you'll find that it is comparable in accuracy, even with the same bond dimension, with the best tensor network methods. And so I think it means that, and we tested it on many CFTs. And so I think it really means that we finally have some understanding, some analytic understanding of what these tensors are fundamentally from the point of view of the CFT. And by having this understanding, it is going to tell us something very interesting about the holographic dual of the CFTs that we're studying. So we're going to see that every CFTs have a holographic dual. It is not rational CFTs have a holographic dual. This holographic dual may not necessarily be gravitational. When we push this CFT to be an irrational CFT, in that particular case, it spits out something that looks gravitational in a very precise sense. So let's try to go through this. Let's go through this recipe of constructing a tensor network that represents CFT path integral, and from which read up a holographic dual out of it. And that holographic dual, let me emphasize, it is a quantum path integral. So it is not a semi-classical approximation, but it basically spits out a quantum path integral. So I think this is this would allow you to easily go beyond a semi-classical analysis. So okay, so what is the recipe that we're following? So there are 4 steps. Step number 1 is to find this the basic building blocks of the CFT. And it is equivalent to cutting the CFT path integral, the 2D CFT path integral, into pieces. Step 2 is that after you figure out how to cut the CFT into pieces, you realize that you can read off a 3-dimensional bulk from it. This is what I mentioned. This is what I mean by reading off a 3D path integral out of the 2D theory that is completely controlled by the 2D theory for free. And then, many people ask me, how did I come up with this? So step 3, because I'm presenting the story in a reverse direction of how we discovered it. So step 3, I'll tell you that the reason why we knew the answers in the first place was because we were actually solving an RG fixed point problem, which is in the work we did in 2022 with Cho and Kai-Ching and others. So we'll tell you how this came from step 3. And finally, we push this program through the Liouville CFT and show how some kind of gravitational path integral is spitted out from the CFT. So step 1 is to cut the CFT into pieces. These pieces would be the tensor network building blocks that I have been talking about. So cutting and gluing in CFT is not something new. In 2-dimensional CFT, we are very used to cutting, decomposing a path integral into a closed pair of pans and cylinders, and then if you want to recover the CFT, you can glue these cylinders and closed pairs of pans together and recover path integral of the CFT in any Riemann surfaces of any genus, and so on, right? So this is not something that is so surprising. But what we're going to do when we talk about cutting, we're going to take one step further. Rather than decomposing into closed pair of pans, we're going to do a decomposition of the CFT path integral into triangles. You can see that there's this kind of decomposition. I think it is new, but it is kind of different from the closed pair of pans decomposition in the sense that, as you can see that here, every single cut, the size of this cut has to be as big as the width of this part of the surface. Whereas in this case, where I cut the CFT into triangles, I can be as fine-grained or as coarse-grained as I wish. So this cut actually knows some more about the CFT than this cut, or at least you can see that this cut, I can control the size of each triangle, and each triangle really might know nothing about globally what happens to the CFD. So fundamentally, it is a way more fine-grained way of cutting the CFD. What are these? So I say cut the surface into triangles. What exactly are these triangles? So I have to compute it. And so now I'll tell you what these triangles are. These triangles has 6 labels. The corners, you should think of it as slightly regulated little, you should regulate the corners by a small segment. And so this triangle actually has 6 edges. And the corners are conformal boundary conditions of the CFD. And the edge between 2 corners is actually a boundary changing operator between these 2 conformal boundary conditions. And this triangle can be mapped to a 3-point correlation function of boundary changing operators on the real line of the half plane. So this triangle is basically related by a very precise conformal map to the 3-point correlation functions of the BCFT. And that's why I call this the BCFT Lego. And so, okay, I claim that these triangles, and for simplicity, or in actual computations that you find in our paper, these triangles are right-handed triangles so that you can easily put them on a surface tile them on a surface, or on a flat surface. Sorry? My surface is, it can be generalized to a non-oriented case, but I also, we didn't really do that in our paper, so I'm not talking about it. It's all oriented. Okay, so I claim that this is a piece of Lego that would be used for building up the CFD. So now let's build up recreate the CFD path integral. So we put the triangles back in. And what is the usual way of gluing, how do I glue 2 triangles together? So 2 triangles would have to share an edge. And so using the usual rule of cutting and gluing in a path integral, it means that if you want to glue 2 triangles together, you just have to sum over all the boundary changing operators that is labeled at this edge, sum over all of them. Primaries and descendants, sum all of them, then you would be able to glue 2 triangles together. After you have glue all the triangles by the edges, you realize that this almost looks like the original path integral, but not quite. Why? Because you can see that several triangles can share the same corner. But remember, the corners are actually regulated peaks of conformal boundaries. So when they share the same corner, what it means is that this is actually a small hole labeled by the conformal boundary condition of a CFD. So this path integral, after you glue all the triangles together, is a path integral on a surface with zillion holes. So this is not yet the CFD path integral that you want. So the next step is, how do you close these holes? If I am able to close these holes, then I return to the CFD path integral. To close these holes, we have to make use of this so-called stringable boundary condition that Gabriel and I proposed in 2020. So the idea was actually very, very simple. So let's try to think of diagonal CFD, diagonal rational CFD as an example. For every boundary condition, every conformal boundary condition, it is the boundary condition of the open CFD, but it has a dual, when you form a hole, a closed hole. This hole, you can think of this boundary condition from a dual point of view as a closed state, and which is so-called Carty state. And the Carty state can be written very explicitly in terms of a sum over Ishigaki states. So the thing is, if I have a hole there, how do I close it? If the hole is filled up by a vacuum state, then it is as if there is nothing in the hole. It is a smooth piece of path integral. And so in that case, if I can fill up the hole with the vacuum state of the CFD, then I would say that this hole does not exist. It is essentially smooth. But then instead, we have a conformal boundary condition, which is labeled by this, which is given by the Carty state. So the reason why it looks like hole is that it is not filled up by the vacuum state, but instead by the Carty state. So how do we turn it back into the vacuum state is the question. So we gave a very naive prescription. What we thought at that point is that, okay, if Carty state is a sum over Ishibashi state, and Ishibashi state, if you know, is the sum of a primary state with all the diagonal descendant states. And so we thought that if we want to fill up the hole with a vacuum state, the closest thing that we can do is to take a linear combination of the Carty state with a certain weight. This weight would be related to, so this S, a modular matrix of the CFT, and you take this particular weight, SA0, so is a component of the modular matrix, which is also proportional to the quantum dimension of the primary sector A. So take this weight and sum over the Carty state. When you do a sum, you replace A by this sum, you immediately realize that SA0 and SBA, you sum over A, you get a delta function because S is a unitary matrix, you get delta V0. And so what it means is that when you do a weighted sum of the Carty state, it would select out the vacuum Ishibashi state. Now, you have a small hole. The hole is very small. So in the dual closed channel, it is as if the hole is weighted by, or is involved by e to the minus the conformal operator. And so this vacuum Ishibashi state starts with the vacuum state. But the next state is basically L minus 2 bar acting on the vacuum state. And so that state has conformal dimension equals 4. And so if I make the hole very small, it would be strongly suppressed in the closed channel. And so as long as if I take the limit that the hole is going to 0, and I take the sum of the Carty state, then I realize that I would be having the Ishibashi state, but only the leading term of the Ishibashi state, which is the vacuum state, is contributing to the path integral. The descendant states are strongly suppressed by exponential in 1 over epsilon. And so I can be sure that this holes would close in the limit that they are going to the 0 size limit. And so this is the way so if you believe me that the path integral can be reconstructed from these triangles, then I have a formula for a generic path integral on some arbitrary surface. So what you do is cut the surface into triangles, replace each triangle by the 3-point function, and then for every single hole in this triangulation, put this particular weight in. These are regularizations for that you need as the hole goes to 0. No, I'm not talking about it here. And so I will have to sum over primaries, sum over descendants, and sum over all the labels, the conformal label on the holes. And finally, take the limit that the holes goes to 0 side. And this should recover for you the path integral on a smooth surface. So I've cut the surface into triangles. So in what sense have I recovered, have I got something that is as good as the tensor network numerics have got? You would have thought that, okay, if I think of this triangle as a tensor network, then this is an infinite dimensional tensor network because you have to sum over all the primaries and descendants, there's an infinite number of states. So this sounds like I have got some kind of tensor network that has infinite bond dimension. But in reality, because descendants have larger and larger conformal dimensions, they are exponentially suppressed. So this is what we did in this paper with Cheng Gong and Zheng Cheng and Chen Ling, is that we tested out this proposal in the Ising CFT. More recently, we have generalized it to some other rational CFTs with and Cheng Gong really did lots of the heavyweight numerical computation. We keep only 2-3 descendants, and it already recovered the CFT results to let's say 3-4 significant figures. So it tells you so what the bottom line is, we did not need bigger bond dimensions than the best tensor network computations actually kept. You only need to keep 2-3 descendants, and the result is as good as the best numerical results. And so that tells you that we have found the right basis for describing CFT in these pieces of tensors. So that you can find very detailed numerical checks there. I will not go into further detail, but the power of this is that not only it is computable analytically, even though these tensors look like it is an infinite-dimensional tensor, you don't need all that much bonds. A few of them is already extremely good for any reasonable computation. Okay, so cut the CFT into pieces. So what? So second is that once you have so in this second step, I will show you, once you have cut the CFT into triangles, that is already enough information to allow you to read off a three-dimensional bulk path integral out of it. How do you do that? So as I mentioned in the previous slide, the path integral of the CFT is now written as these three-point correlation functions, some weight, this is a regulator, and then I have to sum over all of these primary indices, conformal boundary indices, and descendant indices. Okay. This path integral can be divided into two separate pieces. So when you compute three-point functions, as the textbook would tell us, what you need is the structure coefficients multiplied by the conformal blocks. So this part is basically the conformally transformed object involving x1 minus x2 to the power delta minus delta 2 minus delta 3. This is the conformal part. It's completely kinematics. Of course, it is not exactly x1 minus x2 because we have done a conformal map from the upper half plane to this triangle. But this is basically that part that has no dynamics. It's completely kinematics. Then there is the structure coefficients of the three-point functions. So together, they form these three-point correlation functions. And so now let's separate Z into two parts. You notice that the structure coefficient does not care about descendant indices. It only depends on the conformal boundary conditions and also the primaries of the primary labels of the boundary changing operators located at the edge of the triangle. So now let's take this. This has dependence on descendants, and now let's collect all of these conformal blocks together and sum over the descendants first, because this part depends on descendants, but it doesn't depend on conformal boundaries. So let's sum over the descendants first. And if you sum over all the descendants, this gives you some kind of wave function or function that depends only on the primary labels of the boundary changing operator. Okay, is that clear? And then this part is actually very interesting, but I'll say very little about it at the moment. Then there's the second part, which is formed by the structure coefficients and these weights. You put the structure coefficients and these weights together. So the structure coefficients of three-point functions of boundary changing operators have been solved in this infinite class of rational CFTs. They are related to quantum 6J symbols of quantum groups. So this is just some stuff. And the structure coefficients with this weight, you will see that all the dependence of the conformal boundary conditions lie in this collection of structure coefficients and weights. This guy doesn't care about boundary conditions. So similarly, on this side, we can do the summation of the conformal boundary condition labels first. And then you will end up again with the primary labels. And you can think of this as a wave function that controls the edge labels of the triangles. And finally, to recover Z, you take the overlap of this wave function and this wave function, and trivially, you recover the path integral of the CFT. The thing is, you stare at this object where you have the structure coefficients and the weights, and you sum over the conformal boundary conditions. You stare at this object, and then you suddenly realize that this object is a very well-known object already in the literature. This is a path integral of a TQFT on, so for concreteness, let's say the CFT lives on a two-dimensional surface that is an S2, let's say. What is this object if the CFT lives on an S2? you realize this is a path integral of a TQFT in a ball whose boundary is the S2, where the CFT lives. So what is this TQFT path integral? This is the famous Turaya-Viro TQFT path integral, where in a Turaya-Viro TQFT, what you do is that to define the TQFT, what you do is you cut the TQFT, cut a three-dimensional manifold into tetrahedrons. So the structure coefficients has 6 indices, 3 for the primary labels of the boundary changing operators, 3 for the conformal boundary conditions. These 6 labels is actually geometrically a tetrahedron. And these alpha labels would be the edges on the surface triangles. And this sum over conformal boundaries of this weight corresponds to this tetrahedron. Each of them has a leg that points to the center of this ball. And you are basically, when you sum over the conformal boundary conditions with this weight, this is precisely the TQFT prescription of doing path integral in the interior of this three-dimensional manifold. So the bottom line is the following. When you stare at the CFT path integral now triangulated into triangles, you peel them into 2 parts. One part is the conformal block. The other part is the structure coefficient with the weights that close the holes. And then you just realize that the part that close the holes, these weights and these structure coefficients is actually giving you a path integral of a three-dimensional manifold for a TQFT. Basically, a holographic dual is spit out in the process. And this observation is actually related to a series of recent work on generalized symmetries, where the claim is that a general quantum field theory with some topological symmetries, generalized symmetries, can be realized as a boundary condition, non-trivial boundary conditions of a TQFT path integral in one high dimension. So this is the so-called sandwich construction. Here, we start off from the CFD, and we basically spit out this picture directly from the CFD. And essentially, if you look into the literature, they would tell you that you have to put some non-trivial boundary condition of this high-dimensional TQFD to recover the QFD. They would never tell you what is that precise boundary condition. Here, we basically give a very precise boundary condition. It is the conformal block of the CFD. And then you put this conformal block on the boundary of a TQFT path integral over a ball, then you recover the CFD. So a bulk is recovered from the CFD. Is there any question here? Very good. I don't know the precise statement yet, but what I do know is that so when you do ADS-CFD, you also need non-trivial boundary terms and so on. And I think of them as the boundary terms that you have when you want to define when you work in ADS-CFD. And I have some other evidence. For example, I can also do TD-bar deformation. So this is, I may or may not have time to go into that, but I will be able to show you that this is completely essential to the story. If you don't have this, this is just a TQFT. Correlation length is equal to 0. Once you have this, correlation length is infinity, and it also, this part also controls. If you have if this object has a semi-classical limit, like a large central charge limit, then this path integral has saddle point approximation. And this part, this boundary conditions, completely controls what are the saddle points that would actually contribute. So they are very important. They are like setting boundary conditions. The boundary conditions on the boundary of this geometry that produce for you what is the saddle point in the interior. Okay, so how did we come up with this picture, or what exactly have we done essentially? So what we have done is that what is so special about these boundary conditions omega form of conformal block? they essentially they have solved an RG fixed point problem. So, it is actually quite natural when you want to construct CFT, right? CFT is a fixed point, it's a scale, it has scaling invariance. So whenever you, you know that you can have all kinds of boundary conditions to a TQFT, and none of them needs to, and they don't have to have anything to do with CFT. The fact that this is a CFT must mean that you have somehow solved some RG fixed point problem, and indeed, you have. So what is this RG fixed point problem? So, what we have done was inspired by some work in the integrable model literature. I should say actually also by condensed matter. It is really condensed matter literature. So about 2017, 2018, there is a series of papers that made the following observation. That's a large, an infinite class of integrable lattice models in 2 dimensions can be written as some non-trivial boundary conditions of a TQFT ground state wave function. And as you know, a TQFT ground state wave function can be prepared by doing a path integral in a solid manifold, filling up the interior of this 2-dimensional surface. So it's basically if you have, if you want to have the lattice model defined on S2, then this is again precisely the path integral on the solid ball that we were talking about. But here, this is a purely lattice model. They observed that many famous integrable models, such as the Ising spin model, big RSOS models, they can somehow be written as the ground state as the boundary or condition of some non-trivial TQFT. This set of TQFT is precisely the set of Liouville TQFT that I was describing in the previous slide. And omega n, very specially, is a direct product state, it's a tensor product state. And they just show by example by example, they said, they look into Baxter's book, and they just find that if for every single RSOS model, for example, you can just find some tensor product state and put it on top of the Liouville ground state wave function, and somehow it would reproduce exactly the transfer matrix of these lattice integrable models. And so I asked them, is there a way to understand this omega n? And they said, I don't know. You just look at Baxter's book and it works. You always can find this tensor product state. Then I thought, or they also thought at that time, even though they didn't try harder, and we tried super hard for years, is that this is a lattice model, and many of these lattice models have continuous limit. They have, if you tune the couplings. So let's say in the Ising spin model, you can pick this to be the Ising, a TQFT related to the Ising tensor category, and then this is some particular boundary conditions which depends on the temperature of the spin model. So if you tune the beta to a critical temperature, then this would basically have in the thermodynamic limit recovers for you the correlation functions of the Ising CFT. And by the way, how did they pick this part of the TQF, this part of the wave function is based on what kind of topological symmetry the lattice model is believed to have. So this is basically making the topological symmetry of the CFT of the lattice model completely explicit. Okay. And then so at least when this is tuned to a critical point, when the coupling is tuned to a critical point, this would describe a CFT. So I'm interested in CFT. I don't really know much about lattice integrable. Much about lattice integrable model. What I care most about is the CFT. So maybe I can directly work. So how do I think about this problem if I'm only interested in the CFT? The way is the following. This wave function of a of the TQFT assumes that you have already triangulated the ball in a particular way. So in particular, the surface of the ball admits a particular triangulation. So in a TQFT, when you evaluate the TQFT path integral on a closed manifold, of course, it does not depend on triangulations. But if this is a TQFT on an open manifold, then it does have some dependence on the surface triangulation. In particular, different surface triangulations can be related to each other by very simple maps. These are the properties of the quantum 6J symbols that build up this wave function. So in particular, suppose I start with 4 triangles. I look at a subset of the surface triangulations. I started with 4 triangles. It is possible to relate the wave function with 4 triangles locally to another wave function on the same interior, but the surface has changed to only 2 triangles. These 2 wave functions are related up to this quantum 6J symbols. So geometrically, it's like you take this and cover it on top, and the surface triangles becomes more complicated. So these linear maps have geometric interpretations as building up, changing the surface triangulation by putting an extra tetrahedron on top of it. Okay, so it tells you that these are topological wave functions. Different triangulations are not exactly the same, but they're related by very simple, precise linear maps. And so I could start off with a wave function on some very fine-grained triangulation. And then suppose I take take 4 triangles and convert it into 2, it would spit out some numbers, right? So in particular, I can do that globally. So that I start off with a lattice scale of lambda, and after this wave function is related to the wave function with a bigger lattice scale by a linear map, and this linear map would be basically a collection of all of these 6J symbols that is spitted out as I locally turn 4 triangles into 2 triangles. So this is something that is very precise in the TQFT. Now, I started off with a lattice model where I have chosen some particular lattice scale, but then I can always replace this guy by a coarse-grained wave function. By construction, the overlap hasn't changed because this is equal to some linear map times a more coarse-grained wave function. But this guy, I can always group it to omega n and make it flow. Basically, I can take this object, absorb it by this guy, so that it takes you to a new boundary condition that would produce for you the same path integral by construction. So now the thing is the following. If I start with a tensor product state, I replace this wave function by a more coarse-grained wave function, and it spits out a matrix. This matrix gets absorbed by the boundary condition starts flowing. If I repeat this process many times, eventually it would reach a fixed point. Where is the CFT? The CFT, if you manage to get a CFT at all, omega must flow to an eigenstate of this matrix U. So in other words, even though I don't really understand the tensor product state that people started with when they write down this lattice model, I can always say, let's just try to look for the eigenstates of U directly. If I find an eigenstate of this operator U, it defines a CFT for me. So that is the so we started looking into eigenstates of U because we thought as long as you know the eigenstates of U, that is a way of figuring out all the CFTs that has these topological symmetries that is made explicit by this part of the wave function. So that was the logic that we were pursuing. And the conformal blocks, you can show explicitly that it is that omega formed from conformal blocks that we discussed here. You can show it very precisely. This is an eigenstate of this operator U. Then no wonder this is the correct way of recovering the CFT. It's not an accident So what we did was that we figured out the eigenstates of U, but then we worked backwards and asked ourselves, why does this eigenstate of U, based on conformal blocks, actually can recover the CFT path integral? And then we realize that what it is saying, what this whole exercise is saying, is that the fixed point actually tells you that you have cut the CFT into triangles. And the conformal boundary conditions precisely corresponds to the strengthable boundary conditions that we studied several years ago. So that was how we come to this conclusion. So what I discussed previously about rational CFT. And then we got very excited because that U operator that I discussed here, I told you this U operator are formed by these tetrahedrons. They really are related to this tetrahedron. If you look at the what these U's precisely are, it's actually it actually forms a triangulation of a hyperbolic space. And so I thought, and then there's an element of UV in this problem. So I thought this problem sounds like it must be related to the ADS-CFT somehow. And so, so we decided that we really want to, so this is a holographic tensor network. It is a coarse-graining map that is completely determined by the TQFT. And it is a triangulation of a hyperbolic space. We find that very, very suggestive that it should somehow be related to the ADS-CFT, at least in some lower dimensional examples. So we want to find an example to prove our point, yes. Hamiltonian of this lattice model. We're reproducing the classical 2D lattice model. So if you want to recover the quantum Hamiltonian, then you take a small slide, the transfer matrix, and then if you also take the limit where the slides get very long and very thin, then you can read off the quantum Hamiltonian of this 1 + 1 dimensional quantum model. So we have the transfer matrix, but then to read off the Hamiltonian, you have to work a bit harder. Sorry. Many. I think there's an infinite number. Yes. And then, very interestingly, another interesting physics point is the following: that all these topological gapped boundaries of TQFT, you can use that to construct eigenstates of U. They will form topological subset of eigenstates of U. And what is the CFT? Every single CFT will find that it is a phase transition point between two topological fixed points, two topological eigenstates of this U. It is every topological boundary conditions for the condensed matter audience, it corresponds to some anion condensation of the bulk. And the CFT fixed point is always at the point where the condensed anions just didn't condense between two different phases. It's a phase transition. The CFT, let's say the eigen-CFT, it is the phase transition point between electric and magnetic boundary conditions. And so there is something that is proposed by Kong Liang and friends and Zheng Hao. Previously, they were saying that there is some kind of wick rotation of this gap boundary conditions of 2 + 1 TQFT. It would correspond to, you can use the wick rotation and turn it into describing somehow to these CFT, and somehow this is a realization of those ideas. But for HEP-TH audience, I think that's not very important. The important part is you can find eigenstates of this. They are phase transition points between topological fixed points, and they and the solutions are conformal blocks. So lambda is the lattice scale, and it's starting off with the I should not call it n maybe. Suppose you start with a tensor product state, a very simple boundary conditions, and then if you absorb U that is split out by the wave function, then I call that, I just want to distinguish the float boundary condition from the parent boundary condition. So the float one, I reduce it, maybe I should increase it, I don't know, it sounds a bit stupid. This n is just to a label to distinguish flowed boundary condition from their previous generations before they start flowing. So supposedly to get to the CFD, you have to apply an infinite number of times when omega n is fine-tuned. So the way, when we first started doing this, we started doing it numerically. And as I mentioned, I can find all the topological eigenstates of this. And then I start to interpolate between these topological boundary conditions. So I just sum over these boundary conditions and change the interpolation parameter and run this. If it is very close to a particular topological boundary conditions, within 3 steps, you get to the exact topological boundary condition. If it is, and then as you change the interpolation, after a while, as the interpolation parameter becomes very big, then it would run into the other topological fixed point. So that would be a point where it is not sure what to do. That's the CFD. So that's how we reproduce the critical temperature of a large class of CFT, just numerically playing this trick, and then trying to, and I have to say that this story has high dimensional generalization. Cassim is working super hard on it, and to figure out the critical temperature of the Ising, three-dimensional Ising spin model, you can also play the same trick. Okay, but I don't have time. I certainly shouldn't go further into that. The next talk, in the future, in the very foreseeable future, I think Cassim would give that talk. So now let's push this program to an irrational CFT because of our strong belief that it is somehow related to ADS geometry from the RG process. It really looks like it is discretizing ADS space. And so we push it to the Liouville theory. Why Liouville theory is a bit sad? That's because in our program, we need to cut the CFT into triangles. And therefore, one very crucial ingredient is that we need to know the structure coefficients non-perturbatively for the CFD. And there's just too few examples where the structure coefficients can be completely solved because we don't really know how to do path integral for interacting theory. And therefore, these structure coefficients are really solved by conformal bootstrap methods rather than doing honest-to-God path integral. I think mathematicians would correct me because they told me that recently there are breakthroughs, and now, at least for the Liouville CFT, they can obtain these numbers from actual path integrals. But at least when we started, we didn't know about that. And so, so these are things that were guessed by conformal bootstrap, solved by conformal bootstrap by mathematical physicists. And there are just very few other examples, almost no other examples that I can say all the structure coefficients have been solved exactly. Okay, so we pick up whatever that we can find in the literature and start repeating our program. So how do we repeat this program? So in the Liouville CFT, the conformal boundary conditions, there's a closed set of conformal boundary conditions, and they're labeled by this parameter P, which is a real number. Q parameterized is a parameter in the CFD. It controls the central charge. And P is a real number, so from 0 to infinity. So that is a parameter. So that is a continuous spectrum of conformal boundary condition for the Liouville CFD. Then the boundary changing operator between two conformal boundary conditions is also labeled by a complex parameter where Q is fixed by the CFD, and P also goes from 0 to infinity. So now we have a closed set of operators and boundary conditions to play with. What are the structure coefficients? So it was solved by mathematical physicists, and it is related to, again, a 6G symbols of some quantum group given by this group. Okay, so now let's repeat the process of cutting the CFD into triangles. We basically have all the ingredients, but not quite, because we have to close the holes. How to close the holes? So previously, in the previous slide, I said you can close the holes by rotating the Carty state to the vacuum Ishibashi state. That should close the holes. But I cannot say the same in this case. The reason being that the vacuum state is not really inside the CFD. The vacuum Ishibashi state is very problematic. It is not normalizable. The vacuum state is not normalizable. So I cannot just directly repeat the argument and say I rotate the vacuum, I rotate the Carty state to the vacuum Ishibashi state. And so I have to guess how to close these holes. And that is actually a very natural guess. It took us almost a year, but nonetheless, we made we came up with the following guess. So these weights that you put at the holes, there are two interpretations. They are modular matrix element of the CFT. They are also conformal dimension of the label of this boundary condition. So that is something that plays exactly the same role. They are also modular matrix element, and they are also considered as some kind of quantum dimension of these objects, and that's the so-called planetary measure. And so our proposal was we put weights on the holes, and the holes are weighted by this planetary measure. And what you do is that after you glue triangles together, you close the holes by integrating over all the p's, parameterizing a boundary condition weighted by this quantum measure. So how do you show that it is the correct result that will recover for you as if there's nothing there? So we checked that when you only have two triangles sharing a hole, and if you sum over the whole, we look into the precise values of these c's, do the integral combining with the conformal block. You can show that even though I never put in this state called vacuum state, the conformal block is a number, right? Is rotated to the identity block, and so it tells you that the hole is really close. So, so for details, if you are interested in more details of this computation, we can talk about that. But the bottom line is we just checked brute force this way and show that the hole would rotate into the identity block, and therefore in the limit that the hole is very small, it would have the identity block, the leading term would be 1, and so it would not. It is as if the hole is no longer there. So there's some very amazing regularization that goes on just automatically without us worrying about the normalizability of the identity state. Okay. So we have the loop. So now everything is almost ready. We have the Liouville CFT cut into pieces, and we figured out how to close each hole. Then what is the three-dimensional bulk that is fitted from it? Let's take a look. So this is the path integral. We again collect all the structure coefficients and the weight, and we ask ourselves, what is this object? Previously, in the case of rational CFT, this is a Turaya-Biro TQFT path integral over a ball if the CFT lives on S2. Now, what is this? The answer is I don't know, because the Turaya-Biro TQFT is not, nobody has really defined it systematically for an irrational TQFT. Here, in what we have ever done, the TQFT is defined where the number of labels is a finite set. Here, it is an infinite spectrum, and that usual definition of the Turaya-Biro TQFT just doesn't work. So I don't know what is this. Then let's try to figure out what is this. To figure out what is this, we have to take some limit. Basically, to take the large central charge limit of the CFT and see whether this object reduces to something that we're more familiar with. And so to take the large central charge limit, it is equivalent to taking this parameter b to 0. B is related to the parameter q that I described. Q is equals to b plus 1 over b, and central charge is c plus 6q squared. And so when b goes to 0, q goes to infinity, the central charge of the Liouville CFT would diverge. So we ask the following question: is there a limit that you could? What is the limit when the central charge goes to infinity? What would these quantum signature symbols reduce to? And it turns out that there is already a lot of work in the literature about this problem. It's related to the volume conjecture, and people have computed it, and it is related to the volume of a hyperbolic tetrahedron, weighted by some factors of b squared. So unfortunately, when they did this computation, this data is in a different range from the range that we are interested in. Remember, the range that we're interested in is such that this sigma is equals to q over 2 plus ip sigma, alpha is equals to q over 2 plus ip alpha, and p goes from 0 to infinity. Here, it corresponds to P taking an imaginary value, and it is ranged between 0 and pi. So that is actually a parametrization. This volume of a tetrahedron, this parameter here is actually parameterizing the angles between the faces of the tetrahedron. That would be 6 of them. If you have a tetrahedron, that would be every edge is between two faces. And this theta is basically parameterizing the dihedral angle between the faces. But that is not what we want. We want theta, we want to be in a range where theta here is imaginary because our P is real. And we want that range to be 0 to infinity. And then we look for, dig up in the literature, in the hyperbolic geometry literature. And then there's a very interesting, very beautiful formula that relates a function of dihedral angle to the volume of the hyperbolic tetrahedron in dihedral angles. It is equals to the same function, but evaluated on something called L, which is the geodesic length of every edge of the tetrahedron. Now this L goes from 0 to infinity. But then they are related by some L, dL by dV by dL. So L and theta is like a pair of canonical coordinates that are dual to each other. And so there is a transformation between angle and geodesic length. What we have in the structure coefficient, in our structure coefficients in the range that we're interested in this object. But this object itself is not the volume. This guy is the volume. And so the structure coefficient, if we apply the same formula, this V, should be this VL. But VL can be replaced by the actual volume of this tetrahedron with this length plus this factor. Right? So we replace VL by the volume plus this factor. But what is this factor? dVL by dL turns out to be related again to the dihedral angles modeled by 2 pi. And so now we put in, our formula is the following. In the limit that B goes to 0, our 6G symbols should reduce to VL. But VL is really the volume of the tetrahedron plus L times times the dihedral angles between each edge. And then divided by VB is related to the central charge. Am I over time? Let me end this quickly. So I'm so sorry. So now, volume of a tetrahedron. Remember that the integral of the Ricci scalar minus the cosmological constant is also related to the volume of this hyperbolic space. And so this object here, I can replace it basically by the integral over the Ricci scalar minus 2 lambda. And when all the dust settles, the central charge in the ADS-CFT dictionary is related to the Newton's constant by C equals 3L over 2GN, right? So this can be replaced by the Newton's constant. When the dust settles, this object here is precisely the Einstein-Hilbert action. And this part here gives you the Gibbons-Hawking term. And so the Liouville theory is given by giving appropriate boundary conditions to a path integral, at least in the central charge going to infinity limit, given by a path integral over hyperbolic geometries weighted by the Einstein-Hilbert action. If this Gibbons-Hawking term only appears when there is conical singularity in this sum over geometry. This would be this is just something that is spit off from the CFT. I think I've run out of time, so let me just shut up and go directly to the conclusion. So I did not prove ADS-CFT. People would say that this is not a proof of ADS-CFT in the following sense. We hope that gravity should include black holes and all these kind of things. Liouville CFT has the wrong spectrum. It does not. It cannot possibly contain black holes in this path integral over geometry. And fortunately, if you look into this path integral carefully, you realize that indeed, things like smooth BTC black hole is not part of the sum. So that is a good thing. You don't want them to be there, and for Liouville CFT, and it's not there. And so unfortunately, I will not be able to say anything about black hole information paradox. But I just wanted to illustrate the point that it is possible to find a very precise and non-perturbative and quantum path integral of a holographic dual of CFT by studying the correlation functions of the CFT very carefully and non-perturbatively. And I hope in the future I will be able to say something about black holes. And actually, we have something more to say about PD-bar deformation. And hopefully, we will have something to say, not about gravity, but about high-dimensional TQFT and CFT in the near future. But so let me just end here. I'm sorry for the overtime. Thank you.
Thank you for a beautiful talk. Any questions?
Could you just show us the slides that you didn't go over?
Oh, the slides that I didn't talk about.
Yes,
Oh,
please.
just thank you. Okay, so I started off talking about wave functions, mirror wave functions, and how they are related to the root-taxonomy formula. So what about wave functions? Since we can do path integral, it's very easy for us to do wave functions. Suppose you're interested in the ground state wave function of the CFT on a circle. Then what you do is that you do a path integral on a disk, on a smooth disk for the CFT. That gives you the ground state wave function of the CFT. But then this ground state wave function of the CFT immediately have a three-dimensional interpretation. It corresponds to a three-dimensional integral of this object, a hemisphere, that would give you the ground state wave function of the CFT. And in fact, you can choose the triangulation of the CFT arbitrarily. And we can generate a triangulation that looks like mirror. So initially, you would thought, why do we care about this mirror triangulation? Since this is graph independent, you can triangulate the CFT in any way you wish. It just means that the triangles has different shapes, and you have to tune the conformal blocks accordingly so that the surface is smooth. But then why do I care about putting a mirror tensor network where now I can, so you can see that these triangles, basically, I can form a mirror tensor network quite naturally. And each of the tensor in this mirror tensor network is still these 3-point functions. Why do I care? The reason why you care is that you can ask what happens when I start computing entanglement entropy of this object. Let's say one single interval entanglement. So I pick this part to be region A, this part is A bar, and I try to contract the A bar in the, I try to take two wave functions and contract the A bar. Then you realize that this property that was used in contracting holes tells you that two triangles, they share two edges, and then there's a hole inside, and if you contract, this is equal to the propagator. It can be taken out, and it only leaves behind a propagator of the CFT. And using this property, you'll find that if I try to compute, let's say, entanglement entropy of this region, then there is a very simple reduction of the tensor, almost exactly like what happens in a perfect tensor code that was proposed in happy tensor. Each of these 3-point functions behaves exactly like a perfect tensor, up to the fact that it doesn't reduce to the identity as is prescribed in Tallow and friends. It becomes a propagator of the CFT. And so when I try to compute the entanglement entropy of this region, I realized that the tensors can be contracted, all of them reduced to propagator, and they would stop right at this line. But what is this line? Now this line is precisely a geodesic in hyperbolic space. And so it tells you that the entanglement spectrum is controlled precisely by the spectrum of open strengths that lands on the hyperbolic surface. This is the hyperbolic. This is the RT surface, strictly the RT surface, separating this region from the rest. And so it just tells you, it just gives you the RT formula for free for the Liouville CFT. And in fact, for arbitrary CFT for single interval, it has a universal result. And indeed, except that these lines cannot be interpreted as geodesic in hyperbolic, in three-dimensional ADS space for other rational CFTs. This haptic code structure, this mirror tensor code, this tensor structure basically is preserved when you compute any of the single interval entanglement entropy. So let me just say one more point that you might be interested. I should stop. I'm stealing time by a question. And another thing that you might be interested is related to TD bar deformation. So this hole, as I mentioned, you're trying to rotate it to some kind of vacuum Ichibashi state. So if the hole size is exactly 0, that's the end of the story. That is just the identity, and you close the hole. What if you leave the hole size a little bit non-zero? Then the next term in the Ichibashi state will start to contribute. And that next term is TT bar acting on the vacuum. It's TT bar deformation, and it will happen. And we can show that. So you can try to use the saddle point. So the boundary condition, the conformal blocks that you place on the surface of the TTFT is actually important. Suppose I make the hole size very small, and I ask, in the presence of the conformal block that is stuck to the surface, where is the saddle point? I have to sum over all the primary labels. Where is the saddle point contribution of these primary labels as I make the hole size very small? At the saddle point limit, so this is the hole size, it tells you that the length of these edges, the saddle point contribution, is regulated by TT bar deformation. If you so this is hole size. So it is the hole size, finite hole size is to insert a TT bar in the hole. It is regulated precisely by the TT bar hole size. As epsilon goes to 0, then the edge length at the boundary would approach infinity, exactly as you would expect if you're approaching the asymptotic infinity of ADS space. So we are trying to make this more precise in an upcoming paper. So this was a so this idea that TT bar deformation is related to bringing the UV cutoff to the interior can be made more precise in this picture. It's not, I think it's safe to say that at least in the Liouville CFT, it's not a conjecture. We can make it very precise. Okay, so maybe I should still shut up. Okay. Yes, Icho. Sorry.